In this video, I want to provide a brief overview of where is it we're going moving forward this semester, what is the direction we're sort of tracking in, and what are we trying to build through from now until the end of the semester. So our goal moving forward is to try implementing a shell, right? So when you were working at the shell and you see the learn CLI prompt, and that prompt is then followed by text you can enter, right? So you can write some text, you can input some text here. And let's say we give a command such as, I don't know, cat user share dict words. So this is us trying to read out the contents of this dictionary file, and then you say pipe that into grep, and we're looking for say words that contain the letters A, R in them, right? So grep AR, and so this would be a single command that begins two programs, cat, and it pipes the output of cat into grep. And grep is going to then filter only the words that contain a sequence of the letters AR in them, or I should say more technically, the lines that contain the letters A followed by R in it, all right? And so what we're going to build is a shell that you could type this command into, and it would then invoke whatever system calls were necessary to go run these programs on your operating system and print the results back to you in the shell. So we're going to implement a shell. And in order to do so, we need to understand how do we work with text in this way. So what we're going to spend some time with over the coming weeks is, given this string of text here, right, how do we actually break that down into its constituent pieces, find the structure of it, and then process it or take action on that structure. So just to give you a quick overview of some of the steps that are involved in this, remember, these are all individual characters, right? So this would be an array of characters is one way we could think of it, each with their own index going forward. And the first step is to try and find the natural breakpoints for what we will call tokens of this input. And so our tokens in this case would be, say, cat, and then this path. I'm not going to write it out completely. And then a vertical bar for the pipe, and then the word grep, and then the word AR, right? And so these would be the tokens. And those tokens then are going to be fed into our parser. And what our parser is going to try and do is derive some structure from what it's seeing. So I'm going to sort of make up this structure on the fly, but I could imagine a structure where we have, say, a piped command and one side of the pipe is a regular command, and that command, the program would be cat, and then the args or the arguments would be say an array, and there's only one here, and that would be user words, right? And then the other side of this pipe might be another command, and it would be the grep as the program, and then it would also have args, and its arg would be AR, right? And so there's this process of creating finding the tokens and feeding those tokens into a parser. And so the parser is trying to derive some structure from these tokens. And then we're going to have some evaluation of this structure, right? So our code generation is one way of thinking about this, but we're actually going to be interpreting this, is going to take this tree and then form a plan to execute some programs based on this, and be sure that we're wiring up the output of cat into the input of grep, so on and so forth. All right. So this is a non-trivial process that we'll be moving through, and we'll learn about tokenization and parsing, which are two common tactics when working in textual-based systems. But before we do, and why we just talked about barriers of abstraction is we'd really like to approach this problem with some better fundamental abstractions than we currently have, right? So if we think about some of the abstractions we currently have, in our operating system, we have in the system library some calls like callic and malloc and free, right? There's also realloc. Why don't I include that, realloc? That one's an important one, as we've seen. And down here beneath this, we have memory allocation. Right? And so there's some implementation details for how these things work, right? That our memory allocation library provides a barrier of abstraction through these 4 functions, right? And if all we know are these 4 functions, we operate in terms of those 4 functions, we don't have to worry ourselves with the specific details of how was it that it managed our heap memory and did it in an effective and in an efficient way. Right? But those concerns will become your concern if you go on and take operating systems. You'll implement malloc, callic, and free, and see how that level of abstraction is taken care of. But for our purposes, we're going to treat this as a barrier of abstraction, a building block that we can use to build something else. And so in our previous problem set, right, for TH-sort, this was kind of it. Maybe you created some functions that gave you back a C string from a given input line that grew to expand to the space that was needed. So maybe you broke your problem down into some functions. But what we're going to try and do is create a couple of abstraction barriers that make it much easier for us to work with text and express some of the essential complexity that we're interested in when it comes to text processing at a higher level. So what are we going to see next? Well, the next thing that we're going to talk about is a vector, right? And the next implementation or abstraction we're going to implement is what we're calling a vector. Not in the mathematical sense, but in the programming sense. And we're just going to call this vec, right? And implementation. And the point of a vec is to give us a growable dynamic array of any type. Right? So what does that mean? Any type? That means we can use, we can have a vec of chars, we can have a vec of floats or doubles, we could have a vec of structs. But a vec is going to serve as an abstraction idea that we can use. And you're actually, if you've used Python or JavaScript or a dynamic language, you're used to this idea of having what feels like an array available to you, but grows to be the size that you need and has some common operations on it. So what are some of the operations we might want on a vec? Well, we might want to initialize a vec with some value, or at some initial value function. We might want to be able to get a value out of a vec by index. And I'm just going to use some high-level English here. We might want to set by index. We might want to append a sequence of elements from one C array into this vec so that it's owned by it. We might want to remove an item from it, right? So we can imagine these are some operations that we might want at this barrier of abstraction on a vector. But what we're going to see when we get into the implementation details of actually doing this in C, as you all saw in the memcopy function of the last lecture, you have to really do some gymnastics on the typecasting of void pointers to the specific type of pointer you want in order to work with types generically and to copy types generically. So this is going to serve as a base layer implementation for our string, right? So we're going to have the idea of a string, which we're just going to use the name capital STR. And the string then will think in terms of operations like concatenation. And it won't be generic for any type of data. It will be specifically a vec of characters. We might want an operation such as index of, so we can find the index of some character. And some of the methods that you're used to seeing in a string class in a language like Java or Python or TypeScript, you can imagine as being parts of that abstraction barrier. In thsort, you all know that not only did you have to grow a single line of strings, but you had an array of string pointers. Well, here we could imagine having even another layer, which is, say, a vec of string, which provides another barrier of abstraction and allows us to build up a dynamic array of strings, right? And so because we're building on top of this vec implementation, which will give us a growable dynamic array of any type, and that's going to take care of some of the implementation details of like, well, what happens when we run out of space, what happens when how do we free the space, how do we keep track of how many elements we have, things like that. So the memory level concerns of the vec are handled there, so that when we get to the point of thinking about, well, what do we need to offer as an interface for a string or a vector of strings, allows us to express those ideas in much simpler forms in terms of the operations of a vec itself.